Welcome to The Explainer. Today, we're going to dig into the hidden science that shapes the surface of rivers and canals. It's this constant battle between forces, and it creates these really elegant, sweeping curves you see on the water's surface, curves that are anything but random. All right, let's kick things off with a question that seems super simple, but the answer is fascinating. Why isn't the water behind a dam perfectly flat? Like the water in your bathtub. Instead of this level pool, it makes this long, gentle curve. So what's the deal with that? Well, the answer is this phenomenon called gradually varied flow, or GVF for short. This is the whole reason for those long, gentle curves you see near things like dams, weirs, or even just when the riverbed changes shape. So what exactly is this thing? And why do engineers, the folks designing our canals and flood control systems, care so much about it? Let's break it all down. Chances are you've seen GVF in action all over the place without even knowing the name for it. That rising curve of water stretching upstream from a dam, that's called a backwater curve. Or that gentle dip in the water as it gets close to a drop-off, that's a drawdown curve. Basically, anytime the water's surface isn't running perfectly parallel to the riverbed, you can bet GVF is the reason why. Okay, so to really get a handle on what gradually varied flow is, it's actually super helpful to talk about what it's not. Let's put it side by side with this more ideal, perfect world idea called uniform flow. So, on one side, you've got this textbook concept uniform flow. The water depth is totally constant, everything is perfectly parallel. It's a nice, simple idea for calculations, but it almost never happens in the real world. On the other side is reality, gradually varied flow. Here, the depth is always changing, which means the water surface has its own unique curve. And the most important word in the name is gradually. We're talking about slow, drawn-out changes that happen over really long distances, not something sudden and dramatic like a waterfall. The amount of water moving is steady, but its depth is always adjusting. So how in the world can we predict these curves? I mean, it's not just guesswork, right? Absolutely not. Engineers use this really powerful formula called the dynamic equation of GVF. And I know it looks a little intimidating, but the idea behind it is actually just a big old tug of war between competing forces. Seriously, you can forget the scary math for a second. Just think of it like this. The slope, or the shape of the water's surface, is basically just one thing divided by another. On top, you've got the forces pushing and pulling on the water, and on the bottom, you've got a description of the water's current mood, or its flow state. So let's look at those driving forces, the top of the fraction. This is where the tug of war happens. On one side of the rope, you have the bed slope. That's just gravity, trying to pull the water downhill. And on the other side, you've got the friction slope. That's all the energy the water loses from rubbing against the riverbed and the banks, which tries to hold it back. Whichever side pulls harder decides if the water is going to speed up or slow down. Now, for the bottom part of that fraction, the flow state. This is measured with something called the Froude number. It's really just a simple rating. Is the flow calm, deep, and slow? We call that subcritical. Or is it fast, shallow, and rapid? We call that supercritical. It's as simple as that. And when you put all those pieces together, you get this. This little formula tells us exactly how the water depth, which is y, changes over a distance x. It's the winner of the tug of war on top divided by the flow state on the bottom. This right here is the secret recipe for every single one of those curves. So, what do we do with that equation? Well, the cool thing is you don't have to solve it from scratch every single time. Engineers have already used it to create a kind of field guide, a way of classifying all the possible water surface shapes, or profiles, that you can find out in the world. And it all starts with the slope of the riverbed itself. Is it a mild slope that naturally wants to create calm, slow-moving water? Or is it a steep slope that naturally creates fast, rapid water? There are even categories for channels that are totally flat, or, believe it or not, slightly uphill. So you take those 5 slope types, you mix in a few other conditions, and what do you get? Turns out there are only 12. Just 12 possible types of curves that can form. That's it. Each one has a unique shape and its own code name, like M1, S2, and so on. Let's take a look at the one you'll see absolutely everywhere, the M1 profile. This is the curve that shows up on a mild slope when something like a dam gets in the way and forces the water to get deeper. This is the official scientific name for that backwater curve we talked about right at the beginning. And we are not talking about a small little bump in the water here. The M1 profile can stretch for kilometers upstream. It's this massive, slow-motion adjustment that the river makes before it can finally settle back into its normal depth. Okay, this is all great in theory, but how do engineers actually, calculate the exact shape of a curve that might be miles long? Well, they use a really practical step-by-step process called the direct step method. It's a fundamental tool in hydraulic engineering, and it's perfect for channels that have a nice, consistent shape. So here's the game plan. You start at a spot where you already know the depth, like right at the dam. Then you just take a small step, you pick a new, slightly different depth, and then you use the big equation to calculate how far along the river you'd have to go for that change to happen. And you just repeat that process over and over, adding up all the little distances to map out the entire curve, one segment at a time. And this really drives the point home. Understanding all of this isn't just some abstract thing for a textbook. Pretty much any major project involving open water, we're talking designing canals, predicting where floodwaters will go, building safer bridges, it all comes down to being able to compute these GVF profiles. So the next time you're out and about, maybe driving over a bridge or walking along a canal, and you see that water backing up behind a dam, take a second look. Because now you know what you're really seeing. It's not just water. It's that invisible tug-of-war between gravity and friction, playing out right in front of you, shaping that elegant, predictable, and gradually varied curve.